So to help you guys review for your final exam coming up, I put together a final exam review that includes one problem from every section that could possibly be on your test. So your test is going to be from chapters 4 through 9 for the final exam. And so again, I just chose one question that I felt like was really a good question for that section. And if you would like the answer key, or if you would like this handout, just email me and I can get that for you. Okay. So on this first problem, it says in a group of adults, some own iPads and others don't. We have 2 adults that are selected at random, and how many different outcomes are possible? Draw a tree diagram for this experiment. So the first thing that I want us to think about is there's the 2 adults that are being selected. Some own iPads and others do not. Okay, and so the possible outcome, since there's 2 adults, is yes and yes. We could have a yes and no. We could have a no and yes. And we could have a no and no. So what a tree diagram would look like is adult 1 would be our first branch. Okay, and adult 2 would be our second branch. And our question is, do you own an iPad? So our first set of branches would be yes and then no. And then for our adult 2, our second set of branches would also be yes and no. And as you travel on these branches, you get these 4 outcomes here. So 4 is our answer. Okay. And this is just to start getting you to think about all the different possibilities for probability outcomes. Okay, that's kind of where chapter 4 is going to start for us. Okay. All right, on problem 2, this is from the next section. In a sample of 500 families, 50 have an income of less than 40,000, 180 between 40 and 80,000, and then it just says the remaining families more than 80,000. Write a frequency distribution table for this problem. So our actual variable of interest here is income, and it gave us 3 income brackets. It gave us less than 40,000. It gave us between 40,000 and 80,000, and then more than 80,000. We then are going to have our frequencies. Okay, so here's 50. Here's 180. Now, if I have 500 total families, okay, I can find what's missing by adding up 50 and 180 and subtracting from 500, and you end up getting 270 when you do that. And then it also wants us to calculate the relative frequencies. Well, the relative frequencies is just the frequency over 500. So I'll give that first example. So 50 over 500, relative frequency would be 0.1. Okay, the next one would be 180 out of 500. That's going to give us 0.36.
I think 10% is their
and then 270 out of 500
I think it's something we could probably take
is 0.54. And you can always make sure you did this correct, because if you add up your relative frequencies, they should add to 1. Okay. There was a second part to this question. Suppose that one family is chosen at random from the 500 families. What's the probability that this family has a yearly income of less than 40,000? Well, we can look at this as that outcome out of the total, which we got that relative frequency of 0.1, which is 10%. For more than 80, we're going to do that same thing. So that outcome out of the total, decimal answer, percent answer. And this is real life of quarantine situations. Me and my husband are both working in our office right now. So sorry if you can hear him in the background. I apologize if that's distracting. All right, problem number 3.
There's
We have 500 randomly selected adults who drink coffee, and they're asked whether or not they like their coffee with or without sugar. We have 500 adults, 290 are men, and 200 drink coffee without sugar. Of the 200 who drink coffee without sugar, 130 are men. And then the question is, are the events man and drinking coffee without sugar independent? So the first thing that I'm going to write is what it means to be independent. Independence means that the probability of A should be the same as the probability of A given B happens. Essentially what it means is it doesn't matter whether or not B happens. A is just going to continue to be the exact same likeliness. An example is like rolling a dice. If I roll a dice, I get a 4. I roll it again. It doesn't matter that I got a 4 before. Okay, those are independent events. The other thing that I like to do in this problem before we get into independence actually is show you guys kind of how we could create a joint frequency table off of what's given. So we are going to assume men and women for 2 genders here, and sugar and then no sugar. And I know that my total is 500. Okay, my total. And it says in the problem that 290 are men, so that would be the total here. And I could subtract those to get my women total. And I'm just going to put that in parentheses just because that's not something that's given to us. Okay, it's something that we could find by the fact that I know the total is 500 and that 290 are men. It also says that 200 drink coffee without sugar in the 500 adults, right? So no sugar is 200, which means I could find the sugar amount would be 300 because this row has to add up to 500. This column has to add up to 500. So I kind of know the totals already. It gives us more information. Of the 200 who drink coffee without sugar, 130 are men. Well, then that means here 70 must be women, right? I then can add up in this column because I know that my rows have to add up to each other too. So that means that this must be 160 and this must be 140. Okay, and so that's really important to just be able to organize the data and see which pieces are subgroups of the other and which parts are total, right? So what are kind of like our AND events, right? Our AND events are going to be the things in here, right? Our union or our intersections, sorry, are going to be what's in here. All right, so let's talk about now independence. So on this question for independence, I want to know what's the probability of man and drinking coffee without sugar. Are those independent? So is the probability of man, is that equal to the probability of man given no sugar? Okay, well the probability of man in this sample would be 290 out of 500. Is that equal to, now this is given no sugar, so I need this given no sugar piece right here. I need that conditional piece. And then the man within the no sugar, right? Because this right here assumes that no sugar matters. So I need to make that my denominator, and then man goes up here. So if I put this in the calculator, I get that this is 58%, and I get that this is 65%. These are not equal proportions, okay? So they are not independent. Now, what does that mean? Okay, what that means is this does not follow the same proportion of men. In fact, there are as a higher percentage of men in the no sugar category than men overall. So men are more likely to not want sugar in their coffee than women, okay? According to this example. I don't know if that's true or not, but according to this example, that's what it's saying, okay? All right, let's continue to talk about some things when it comes to conditional probabilities and independence, okay? So a company is to hire 2 new employees. They have 8 candidates, all of whom are equally qualified. Of these, 5 are women. They just take 2 persons at random. What's the probability that both of them are women? Well, the thing here, because we only have 8 candidates, is this is a small sampling frame. And so when I take out that first woman, right, 5 out of the 8, right, choose one of them would be 5/8. If this is confusing to you, think about this as like the general, like if you had a bowl, right, and 5 marbles are green and 3 are blue, okay? The probability of choosing a green one is 5 out of the 8, right? But once I take that away, my denominator changes, okay? Because my sampling frame is so small, it matters that I took one away. And so I'm going to say, okay, well then I'm going to now only have 4 out of 7 left over, okay? So because our sampling frame is small, it matters that I took one away. So that's going to be equal to 3571, or approximately 36%. Okay, let's look at problem number 5. On problem number 5, it says, in a survey of adults, 40% hold the opinion that there will be another housing bubble in the next 4 to 6 years. 3 adults are selected at random. So 40% have this opinion. We are going to select 3. Now, since this is out of just adults in general, thousands of adults, okay, that we are selecting at random, this is a large sampling frame. Okay, if I have 1,000 in my denominator and I take one out and I have 999 in the denominator, that's not really actually going to change a lot of my fraction anymore. Okay, so when I have a large sampling frame, I'm not going to worry about that denominator piece. I'm just going to go with the probability of success, and we just kind of assume that that conditional probability doesn't really matter anymore. Okay, that there's no dependence on choosing somebody ahead of you. So probability that all 3 adults say yes, there will be another housing bubble would be 0.4 times 0.4 times 0.4, okay, which is 0.064. And then part B, what's the probability that none of the 3 adults, okay, have this opinion? Well, if 40% have the opinion, then 60% would not have the opinion. So we're going to say, okay, well, that would be 0.6 times 0.6 times 0.6. Okay. And so I wanted to include those two so you guys could have an example as you're getting ready for your final of when sample size matters and when it doesn't. When you have a small sampling frame, your denominator does have to change. It matters. Large sampling frame doesn't matter. Just multiply straight as it is. All right, another example from chapter 4 is the addition rule. Okay, so problem number 6 deals with that. There are 600 adults and they are asked whether or not they watch for calories and fat content when they buy groceries. And this gives the 2-way classification on response and gender. Okay, 1 adult is selected at random. Find the following probabilities. So if I look at man and I add up man, so here, here, and here. Okay, and I'm going to add those up and get 300. Or no. So in this group of 600 adults, okay, I choose one person and they're either a man or they say no. So it could be a women and no. Okay, so I'm going to add up my no category as well. Okay, that's 262. But when I do that, when I take 300 and add, 292, I actually included this 168 twice. I included it in my 300 and I included it here. And that's not right. I need to adjust for that. So I'm going to subtract out that intersection. And then I'm going to find this out of all possible outcomes, which is 600.
Yeah, I think it's just how do we know where to set that?
And that gives me 0.7067.
You know, you're wanting to prevent bog and known machine would be my guess. Is why
Now,
you said
if I know this whole thing is 600, okay,
So
then that means that
don't
my
have any
women total must also be 300. That's going to help me on part B. So on part B, the question is yes or woman. Well, I'm going to add up my yes category. Same thing I just did. That's 180. I'm going to add up my woman category. But same thing. If I add up the 180, I add up this. I counted this 106 in both of those categories. I can't do that. I can't count those 106 people twice. I only need them counted once for the 106 that they are. And so then I'm going to divide this by 600. Okay. Now part C is an interesting question because it says no opinion or yes. Well, if you look here, this is my yes column. This is my no opinion column, which has a total of 128. There are no outcomes in common here. These are disjoint or mutually exclusive. Okay, and that's different than independent. Independent means the probability resets every time, okay, and we're not worried about A or B happening, right? There's no dependency. Disjoint, mutually exclusive means something completely different. They mean that there is no intersection. Okay, they can't happen at the same time. You can't have answered yes and no opinion. You just can't do that. So I don't have to worry about that subtraction piece. I can just say, okay, well, that would be 180 plus 128. I don't have any overlap to subtract out. So I don't have an intersection here. Okay, let's look at another kind of question like this. Problem 7. The probability a randomly selected elementary or secondary school teacher is female is 68%, holds a second job is 38%, and here's your and. Okay, so female, male, yes, no. We're just going to assume that those are the only outcomes here, okay? What I'm given is probability of female is 0.68. Probability of second job is 0.38. And your and probability is 29. And so our equation that we're going to say is, okay, probability of female plus probability of second job. And then you're going to subtract out the probability of the intersection. This is the symbol for intersection, which is the and. Okay. But I like sometimes just kind of filling out this table again because I think it follows with problem 6, right? Here's your total for female plus here's your total for second job. But when I had these totals calculated, right, I added 29 twice. So I need to subtract out that intersection piece. Okay, I only need it to count once. And so that's going to be 77. If you ever do a problem like this and you end up getting a number bigger than 1, you probably didn't do the subtraction of the intersection. Okay, so that's always one way to kind of think about, like, oh, maybe I didn't do this right. Probabilities can only be between 0 and 1. So if you get a decimal answer that's like 1 point something, then you probably forgot to subtract the intersection if you were adding. All right. All right, let's continue looking at chapter 4 questions here. So this is just a continuation. It's not a problem from the book. I just kind of added it in here of that 40% housing bubble question. Okay, so let's think about this because it didn't ask it earlier. 40% hold this opinion and you have a group of random adults. How many different ways can we select 2 that hold this opinion and 1 that disagrees? Okay, this is important when we think about the number of ways that we can choose these outcomes. Okay, so when we're thinking about this, I have 3 adults, right? 1, 2, 3. So let's think about in this three adults, how many ways we could have two that say yes and one that disagrees? Well, it could be this, right? But that assumes order. That assumes that the first two said yes and the third one said no. So we could also have this, and that still has that 2-to-1 outcome. We could also have this, and that also has that 2-to-1 outcome. Okay, so the equation we would use for this is 3 choose 2. It's also written in a combination like this, right? And that tells you the number of ways, if you have a total of 3, that you could have two people say a certain thing. And you can see that that is 3 total ways. Okay, so I use that as kind of an introduction into problem number 9. So in problem number 9, we're at the end of chapter 4. We have 20 stock options, and we're going to randomly select 6 from that 20. And so I'm not going to create a whole diagram of 20 stocks, like that's a lot to draw, but it's the same idea, right? If I were to say these 6, bam, 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 and these 14, no, well, that assumes that that's the order in which you want them, which is not necessarily the case. It's random selection. So in this case, we're going to do 20, choose 6. The equation for that's going to be 20 factorial over 6 factorial times 14 factorial, where 14 is 20 minus 6. And I got that from the book. You can also use your calculator, okay, to do this. 20 factorial says 20 times 19 times 18, all the way to 1. 6 factorial, 6, 5, 4, 3, 2, 1. 14 is 14, 13, all the way down to 1, okay? And so when we plug this into our calculator, we end up getting, there's 38,760 different ways this could happen, which is crazy to think about, okay? Now let's say the order in which these are selected is important. That's called a permutation, okay? And in the question for the final, it would say combination or permutation. You would just need to be able to go and find the equation for that. So the equation for that is 20 factorial. And then I don't worry about that 6 factorial. I just want the 14 factorial. And that's 2,790,000. Oh, nope, sorry, 27,907,200 different ways. Okay, and what it means is even if you had that first 6 and then 14, it matters that you chose that number 1 and then number 2 and then number 3. So like order actually matters in the way you selected the stocks. Okay, so there's 27, almost 28 million different ways that could happen. And that takes us through chapter 4, okay? That's a good chunk of like your intro to probability questions. And if they're going to be on your final, okay, those are the different ways that you need to be able to access that information. All right, looking at problem 10, according to a survey, 14% of motorists are uninsured. Suppose that currently 14% of all motorists in the city are uninsured. We're going to select 2 motorists, okay, at random. Let X denote the number of motorists in this sample of 2 who are uninsured. We're going to find a probability distribution of X. Now, again, thinking about that like small sampling, big sampling, all of those things. This is a large city, so I'm not going to worry about like, does my denominator change when I do this, okay? So let's think about what the values of X could be. And let's think about the probabilities of that happening. So X could be 0. That means that both of them, right, have insurance because X is the number who are uninsured. So this is both insured. 0 are uninsured, right? So that's going to be the opposite of 14. So that's going to be 86 times 86, which is 0.74. We do have the outcome that one of the 2 is insured. Well, we can't assume order. So that could be that the first one is insured, but it could also be that the second one is insured. And those are 2 different ways that we can get that combination of 1. which gives us 24%. All right, the last outcome could be 2. Well, that means that both of them are uninsured. So 0.14 times 0.14 is 0.02. Okay, and then it also wants us to do a tree diagram. So this is motorist 1, this is motorist 2, and this is what we would do. So we have insured, no insurance for the first one. So the probability that they're insured, that's going to be 0.86. No insurance is 0.14. And then we have the second motorist with the same number of outcomes. Okay, and so this could help you too if you wanted to do the tree diagram first. It kind of helps you figure this out, right? Because 0 would be both insured, so insured, insured, 0.86, 0.86. That's exactly what we got right here. One person insured, one person insured. Both of them do not have insurance, okay? All right, let's go ahead and look at problem number 11. This is from the book, problem 519. Okay, the following table lists the probability distribution for the number of patients entering the emergency room during a 1-hour period at this hospital. Find the mean and standard deviation. So I have this nice discrete number of patients per hour, and let me find the mean and standard deviation. So what I need to activate in my brain are those two formulas, one for the mean, which is x times p. Okay, and so that's going to be 0 times 0.2725, and then 1 times 0.345. And I think in class she had you guys like write out like a 1, 2, 3, 4, 5, 6 this way, and then the probabilities, and then this. I'm just writing across. I really don't have a lot of room to do that, but this is what you would do. So you would do that all actually 7 times because you're including 0. So 7 of these. Plug into a calculator or into Excel and you get 1.3. Okay. So then for our variance, I need to add up x squared and then multiply by p of x. I'm going to do that first and then subtract out the mean squared. So here I did make a little table. So that's going to be 0 squared times the probability. This is going to be 1 squared times the probability. Okay, 2 squared would be 4 times the probability. 3 squared would be 9 times my probability, and so on and so forth. Okay, when you add these up here, you get 2.949. That's my summation here. So I get 2.949 minus 1.3 squared. And there I get my variance. Last thing it wants me to find is my standard deviation, which is just the square root of your variance. And that's 1.14 if I just take that to 2 decimal places. Okay, so a little bit calculation heavy on those type of problems, but again, this would be an equation that you would want to maybe have on like a formula sheet that's easy to reference, or you could like earmark in your book for chapter 5, because that's going to be something that's really important to look at. Okay, that's probably going to be on your final. If I had to put some money on it, with a table like this, it was on your midterm question 1. So that same kind of question. Okay. All right, let's keep going. All right, problem 12. Office supply company conducted a survey before marketing a new paper shredder. They say that in this survey, 80% of the people are satisfied. Assume 80% of all people who use the shredder will be satisfied. And on a certain day, 7 customers bought this shredder. So I have in this question, I have a probability of success, right? And I have a set n. And so when I'm given those two things, the thing that we should have triggered in our brain is that this is a binomial model. Okay, let x be the number who are satisfied, find this probability distribution, and then draw a histogram. Well, let's look at all the different possibilities that this could be. Okay, well, if I have 7 customers, it is possible that 0 are satisfied. 1, 2, 3, 4, 5, 6, or all 7. Where I'm going to find these probabilities are going to be in the back of your textbook. So that might be on the online textbook if that's what you use, or it might be the physical textbook if that's what you use, whichever one that you are using. If you have a calculator and you do normal PDF, and you put in this N and this P and then don't press any X value, then it actually will just output the entire distribution for you. Okay, I don't have an 83 or 84 calculator to show you that at home with me. It's the school's and it's up at the school. So, but that's what you would do is you'd go under binomial PDF. Okay, and then you put in your N and your P, and then go ahead and close the parentheses, and it will give you just this list of probabilities here. Okay, and if you have specific questions about that, you can always ask me, email me, come into office hours and figure that out. Okay. All right, the second question says, draw a histogram of this. Well, histograms look like bar graphs. It's going to start at 0, and then I have a 1, a 2, a 3, a 4, 5, 6, 7, and then that bar for 7. Now I need to go all the way up to about 40%. So I'm going to go by tens to get that probability of 40%. Well, 0 is 0. 1 is just a little bit more than 0. 2 is just a little bit higher than that. Okay, so I'm kind of trying to draw in just like heavier things that increase a little bit. Now 3 is 3%. So this would be 5%. I'm going to draw in my 3%. 4 would be 11%, so a little higher than that 10 marker. 5 is going to be 28%, so not quite to that marker. 7 is going to go almost all the way up to 0.4, and then I'm going to go back to 21 for my 7. Okay, and there's my beautiful histogram. Notice it does not look bell-shaped. Okay, it does not look unimodal and symmetric. Okay, unimodal, yes, but not symmetric. Look at the skew to the left right here. Okay, but we can still find a mean and standard deviation using the formulas for a binomial. So n times p, 7 times 0.8 gives me 5.6. And standard deviation, npq, and then take the square root. Okay, 7.8, and then 0.2. 1 minus 0.8 gives me that 0.2. And I get 1.06. You could do this the same way that we did problem 11, x times p, the whole way. That'd be the long way to do it. If you realize it's a binomial situation, which you had to do to set it up to find out probabilities anyway, then you should just use those equations, okay? All right, part C says, what's the probability at least 4 of the 7 customers will be satisfied? So at least 4, the least I want is 4. So x greater than or equal to 4. Well, I can just use my distribution output table here and add up those outcomes.
Like you said, down to reduced.
And that's 97%. So pretty likely that of the 7, at least 4 will be satisfied with the new shredder. Okay. All right, so that's a good binomial question. Ties in a lot of the things for that section, which is why I chose that, okay, to review with you. Looking at problem 13, okay, a really bad carton of 18 eggs has 7 that are spoiled. An unsuspecting chef picks 4 eggs at random for his mega omelet surprise. He might be very surprised. Find the probability that the number of unspoiled eggs among the 4 selected is. And I think actually in my answer key, I did it as spoiled. So I'm going to change this to spoiled. So just change this. I want this to match the answer key that I'm going to post. So change this to spoiled eggs. Okay. All right. So for the spoiled eggs here, okay, we are going to look at 18 first. So out of this 18, I have 7 that are bad, which means I have 11 that are good, right? And all of my outcomes here are going to have a denominator of, out of this 18, choose any 4, right? That's going to be my denominator for every single one. So I'm going to write that for my denominator for every single one. 18, choose 4. We'll do this one here in just a second, okay? But that's going to be my denominator. Now, if it's exactly 4, then out of the 7, then 4 were bad, right? So 7, choose 4 times, well, that means that out of the 11, I didn't choose any of them, okay? And that probability is 0.1078. Okay, 0.1078. All right, looking at number 2, 0 or 2 or fewer would be the outcomes x equals 0, x equals 1, or x equals 2, right? So all of these denominators, again, all of these denominators have this out of the 18, choose 4. That's the total number of ways I could choose 4 eggs out of the 18. Then for each one of these, I have the 2 groups on top. Okay, 7 and 11 are what I'm choosing out of. So on this first one, if I want 0 spoiled eggs, so that means that 0 are bad, well then all 4 are good. On the second one, if 1 is bad, then that means 3 are good. And if 2 are bad, then 2 must also be good. I'm then going to find those individually and then add those probabilities to each other. And when you do that, you get 5147. Okay? All right, part C is now more than 1. So I have 2 options that I can do for more than 1. I could do 2, 3, and 4, okay, which is the option that I think I'm gonna go with, or I could do 0 and 1 and then just go from there, right? Because if I want more than 1, then that's the probability x is greater than or equal to 2. Well, if I have these outcomes, if I have 0, 1, 2, 3, 4, right? Those are my values of x I can choose from. I want these outcomes, 2, 3, 4, for this problem. But all of these have to add up to 1, right? So I could do this, 2, 3, 4. I know 2. I know 4. I would just need to find 3, right? Or if I find this, which I also know right here, okay, then I can do 1 minus this value and it would give me this, which I think that's the route I'm actually going to do. I'm going to go off of what I just said. Okay, and so I need to actually figure this out. I don't know why on my key I didn't end up doing it. So 7 choose 0, sorry, times 11 choose 4. And I'm going to add that to 7 choose 1 and 11 choose 3. Okay. So this is 0.4853, which means I want to do 1 minus to find the complement. Right there. Okay. Now this as a distribution, okay, this as a distribution is called hypergeometric. So if you're wanting to look in the book to look at more examples or whatever the case may be, that's what you would do. But I kind of follow a similar outline as to what the professor uses in class, which is I take up my total, I break it in there, and I'm like, oh, I'm choosing from each one. So I'm looking at the combinations of each in the numerator and then the total combinations in the denominator. And that's what I choose to do for this question, okay? All right, let's look at problem 14. So on problem 14, okay, it says an average of 5.4 shoplifting incidents occur per week at an electronics store. Find the probability that 3 or more such incidents occur in a given week. So notice I'm not given a percentage of this happening. I'm not really given like a set n. I'm not really given like subgroups of an n. This is a different type of situation. I'm given an average, which I'm going to call this average lambda, just because I know that that's what we're supposed to call it, okay? But I'm given this average, and then I want the probability of 3 or more. Well, really, sadly, our outcomes go from 0 right on. Really, I could have 10 or I could have 20, right, that occur in a week. That'd be a very bad week, but I could. I just know that the average is 5.4. Well, I could continue technically on and on forever. So if I want the probability of 3 or more, and that's the probability that I want, then that would be the same as finding these probabilities right here, and then doing 1 minus that, okay, and that would find me the other side of that distribution. Okay, so I'm going to use what's called the Poisson distribution in this example, and the reason I know this is because I have that average and my x values go from 0 to essentially infinity. Okay, and so I need to be able to have a distribution that does the same thing, which is why we use that e. So that equation is 5.4 to the 0, lambda to the 0, e to the negative lambda, all over x factorial. And I'm going to do that for 1. And I'm going to do that for 2. Okay. And once I find that, I'm going to take that and then I'm going to subtract that value from 1. And you end up getting, I just have the final answer here. Let me go ahead and find it real quick. Okay, so you end up getting that this is 0.0948. And so when you do that 1 minus, you get 9052. So we have like a 91% chance at this store that 3 or more shoplifting incidents are going to occur, and only a 10% chance that it's going to be less than 3. That doesn't seem like very good odds in our favor of the store, but based on the data, that's our distribution probabilities, okay? All right, that does it for chapters 4 and 5. And I think what makes 4 and 5 so tricky is that every single section in 4 and 5 is a different type of distribution, right? It's a different type of probability. It's a different type of calculating outcomes. And so if you need more support on those 2 chapters that are definitely going to be on your final exam, I would say go back through those reviews for midterm 1 and midterm 2. Go back through and look at the videos that I've posted on those 2, because that's going to be a hard hit if you don't review those for your final exam, okay? We're now going to get into chapter 6, which is a little bit more streamlined. Okay, so chapter 6 is all about a normal distribution. So here on chapter 6, okay, we have the average mortgage payment. Okay, suppose that they follow an approximately normal distribution. So that's one thing that you're going to know that it comes from that chapter, is that it's going to say follows a normal distribution in the problem. You have a certain mean and a standard deviation that's given. Okay, and we're going to try to find these probabilities here. Okay, now normal distributions can follow a continuous distribution. Okay, so we're going to be looking at a distribution that looks nice and pretty and bell-shaped. And I'm trying to find these likelinesses right here. So here's our mean. So this first one is less than $1,200. So I need to look at, this is my distribution, okay, with my mean here in the middle. How far away is 1,200 from that center? So I'm going to find that by doing a z-score. So z is equal to 1,200 minus the mean all over the standard deviation. And I end up getting negative 3.93 standard deviations below the mean. So 1,200 is like all the way down here. And when you try to go find that on the table, you end up getting that probability is really stinking close to 0. Like, it's not going to be very likely that you find a mortgage payment in this city of $1,200 or less. Okay. Part B says between 2,300 and 3,140. So I need to find 2 z-scores here. So z1 would be 2,300 minus the mean all over the standard deviation. And you end up getting negative 1.31. When you do the similar calculation for z2, so 3,140 minus the mean over the standard deviation, you get 0.69. And so when I look at where these values are compared to the mean relative to the standard deviation, I have z1 that's down here, and then I have z2 that's a little bit closer to the mean. And that's the area that I want. Okay, when you find the larger probability and then subtract out the smaller probability, the probability that you get is 65.99. All right, more than 3,600. So let's figure out where 3,600 is compared to the mean relative to my standard deviation. And I get that it's 1.79 standard deviations above the mean. So if I look at my distribution, here's the middle. 3,600 is 1.79 standard deviations above the mean, and I'm looking for more than, so I want that right-hand side. Now be careful when you go look in your table, you're going to get something that's about 96%. Remember, that's the left-hand side always in that table. You want the right-hand side, which gives us 0.0371. All right, and then part D, between 3,200 and 3,700. So I need to find 2 z-scores again because I have 2 data values that I'm looking at. And I end up getting 0.83 for my z1. When I do that same calculation to find z2, I get 2.02. Here's my center, so z1 is not even 1 standard deviation away. Z2 is 2 standard deviations away. Okay, and so that probability ends up being 0.1808. Now, I meant for this problem to be a quick review, okay, not a reteach. So if anything in that problem, you were like, nope, where did you get that? Then you need to go back to some chapter 6 review videos. You need to go back through some of those review problems and make sure that you're really understanding how to find those probabilities, okay? Problem 16 says that the management of a supermarket wants to adopt a new promotional policy where they give a free gift to every customer who spends more than a certain amount. The expectation of management is that after this is advertised, okay, that the supermarket is going to be making money expenditures that will be normally distributed with a mean of 95 and a standard deviation of 20. And they want to give free gifts to at most 10% of the customers. Now remember, they want to give it to the 10% that spend the most. So that 10% on this distribution would have to be up here, right? 10% would have to be up there, which means I'm looking at the 90th percentile for my z-score. I need that positive z, and that positive z ends up being 1.28. I'm then going to plug that into my z-score calculation. So x minus the mean all over the standard deviation, and I'm going to let that be equal to my z-score. I'm going to multiply by 20. I'm going to add 95, and I get that any person that spends $120.63 or more based on this information would get that free gift. Okay. I think right now, maybe with grocery stores being the only thing that's open for a lot of us, I think we would need to adjust our policy. But that's what it is based on the data that they gave us, okay? All right, problem 17 now goes into chapter 7 right here. On chapter 7, okay, we start talking about sampling distributions. So it says here that according to this labor statistics, a financial analyst earns on average this much money, okay, and we have this mean and standard deviation given to us. Find the probability that we have this random sample of 400 financial analysts that makes more than that salaried amount. Now, we have to be careful here because we're looking at if I have a random sample of 400. So I'm not just talking about one person. I'm saying I'm going to take a sample of 400 financial analysts and find the mean. And I want to know what's the probability that the mean of that sample is greater than or equal to this amount right here. Okay, so when we do that, I need to adjust for this sampling distribution. So this is the mean for the sampling distribution. And then the standard deviation for the sampling distribution, remember we have to divide by the square root of n, which ends up being 1500 for our standard deviation. So when I go to find my z-score here on part A, I do my x bar value minus my mean all over the standard deviation for the sampling distribution, and I get a z-score of 1.4. Okay, if I look at a normal distribution with a z-score of 1.4 and I want to find the greater than probability, that probability is 0.0808. Okay. If I want to find between two values, then I would have two z-scores. So z1 would be 109,300 minus the mean all over the standard deviation for this sampling distribution, which is negative 0.81 standard deviations below the mean. Z2, I do a similar calculation. I get 1.89 standard deviations above the mean. which means for any normal distribution, I have something that is negative 0.81 standard deviations below, something that's almost 2 standard deviations above, and I end up getting that that probability is 0.7609. Okay. And so if we have where we're taking samples from the population, okay, then we need to adjust the standard deviation to adjust for the fact that we're now looking at the sampling means distributions, okay, not the entire population distribution. All right, continuing with chapter 7, we have a survey of all medium and large size corporations. Show that 64% of them offer retirement plans. Okay, and then we're going to let P hat be the proportion in a random sample of 50 who offer retirement plans. So again, this might look at first glance like a binomial model, okay, because there is a probability of success given and an N that is given. Okay, but we're not looking at this as like within this one sample of 50, what's going on. I'm looking at if I take thousands and thousands and thousands of samples of size 50 and calculate their proportions, what is that going to look like? So with that, I know that the mean of that distribution is going to be 0.64, and the standard deviation is going to be the square root of P Q all over N. And that's going to be equal to 0.0679. I then can do that same z-score type calculation that I did on all these other problems with this new mean and standard deviation for that sampling distribution of P hats. So my z1 is going to be 0.45 minus the mean all over the standard deviation, and that z-score is negative 1.47. If I do the exact same thing for 61%, that is also below the mean and gives us a z-score of negative 0.44, which means the distribution slice that I'm looking at, okay, is down here completely. I go into my calculator, my normal distribution chart, whatever it is, I find that that proportion, that probability is 0.2590. Okay. Now part B, if I want to know greater than 0.71, I'm going to say 0.71 minus the mean all over the standard deviation. And I get 1.03. So 71% is about 1 standard deviation above the mean. So 71% is about here, and I want that probability. If you go into your chart, you get about 84-ish or something along that lines. And our probability is 0.153. 1513. All right, we do have a few more problems. That is just taking us through now midterm 2. I now have a couple problems for you with regards to chapter 8 and chapter 9. So these would be questions that you have not been tested on yet that will definitely be part of your final exam. So on this problem right here, a city planner wants to estimate the average monthly residential water usage. He has a random sample of 40 households from this city, and they gave a mean water usage of this many gallons. Okay, based on earlier data, we know the population standard deviation is this many gallons, and we want a 95% confidence interval. Well, since we know the population standard deviation, I'm able to do this as a z-interval and use the z-chart. So 95%, when I adjust for this confidence interval, that z-star value that we're going to use is going to be 1.96. For this confidence interval, I'm going to use the equation x bar plus or minus that z-star value, and then I'm going to multiply that by the sampling distribution's standard deviation. When I plug all the values in, this is what that equation is going to look like. And then when I plug this into my calculator, either doing lower bound and upper bound by itself or by plugging into like a calculator program that will do confidence intervals for you, this is the interval that you get for 95%. Okay. All right, let's look at the next problem. A company wants to produce detergents and wants to estimate the mean amount of detergent in a 74-ounce jug at a 99% confidence level. The company knows that the standard deviation of the amounts of all detergents in such jug is 0.2. So standard deviation is 0.2, and I need a 99% confidence interval. Okay, how large should we select so that this estimate is within 0.4 ounce of the mean? So when I think about the equation that I used in 19, the margin of error, this within piece of this question, is just that plus or minus piece. That margin of error equation that I'm going to use is z star and then standard deviation over the square root of n, where now I'm solving this for n. The margin of error is this within amount right here. So I'm going to say, okay, 0.04 plus or minus z star, okay, for that 99% confidence interval is going to be 2.576. And I have 0.2 here over the square root of n. Oh, I said plus or minus. That's not plus or minus. I'm so sorry. This should be equals. Okay, margin of error equals this right here. I'm then going to solve this for n. So I said if this is this number over 1, we can then multiply those numerators and the denominator straight across, just like you would for any fraction. Okay, I'm then going to multiply square root of n on this side, and then at the same time divide by 0.04. And I end up getting 12.88 when I do that. When I square both sides, I then am going to round up. And so n must be greater than or equal to 166. Okay. If you have questions on how I found that p-value, if you have questions on not p-value, sorry, that z-score based on the confidence interval or anything about that question, you need to go back and look at chapter 8 in 8.1 and 8.2 in order to find out how to do those, okay? All right, on problem 21, we're going to start looking at random sampling here. So if we have this random sample of 36 mid-sized cars, and then all that I don't have any population information. I just have the sample information. So I just have this mean and this standard deviation. When that's the case, I don't know my population standard deviation. I'm going to have to use S as that approximation. And when I do that, I'm going to have to use the t distribution. Okay, now my degrees of freedom for that t distribution is n minus 1. And so if you go and you look up in the back of the book, or if you go to the calculator and you try to figure out what that t value is going to be, you get 2.724. Okay, I'm then going to plug into the very same or very similar formula as this, just instead of z, I'm going to use this t star. So I'm going to have my mean from the sample plus or minus 2.724. The standard deviation that I do have And then I'm going to divide this by the square root of n. That's giving me a lower bound of 25.36 and an upper bound of 27.44. Now, if this interval is too wide, there are two things that I can do to reduce the interval. There's two things that I get to control. One is my confidence level. The other is my n. The other two pieces are just random variables. I don't really get to control the mean and the standard deviation. So if I want to reduce the interval, then I can either bring down my confidence level, or inversely, I can increase my sample size. Okay, now those are the two possible alternatives, and then in the question it does say which alternative is best and why. I don't know that there's ever a good answer for that question, so I'm not going to write anything in particular. If you're able to resample and increase your sample size, great. That's probably actually better than decreasing your confidence, but you can't always do that. So I don't know that there's always a best and why. Sometimes you just have to go with like what you're able to do. It might be that we decrease the confidence level from 99 to 98. Like that's not that bad. But a drop from 99% confident to 90% confident, that might be a big deal. So you just have to kind of weigh in. And I don't think it's a black and white answer on which one is best, unfortunately. All right, let's go ahead and look at proportions as well when we talk about confidence intervals. Okay, so we have a problem here that's from Chapter 8. It is said that happy and healthy workers are efficient and productive. A company manufactures exercising machines, wants to know the percentage of large companies that have on-site health club facilities. A random sample of 240 such companies showed that 96% of them provide such facilities on site. All right, so let's try to figure out what that point estimate would be. That point estimate is like, hey, if you had to approximate the true proportion, what would you say? Well, the only thing we could use to approximate it is what we were given in the data. So that's going to be 96 out of 240, which is 0.4. Part B says now construct a 97% confidence interval for all of these companies. So we're going to use this p hat in our equation, and then we're going to add or subtract z star. Proportions can use z, that's just fine. And then the standard deviation that we're going to use, well, I don't have a true proportion here, so I have to just approximate this. So p hat q hat over n. So 0.4 I'm going to plug in right here. Again, if you use technology or the back of the book, you do find that your z star for the situation is 2.1701. And then we have 0.4. Q hat would be 0.6 all over, and n would be 240. Okay, so we're going to do lower bound, upper bound. Lower bound is 33%. Upper bound is 47%. Okay, and that's a 97% confidence interval. So I'm pretty confident, I'm 97% confident that less than half of these companies have on-site equipment. That's essentially what that means. Somewhere between a third and a half of companies have these on-site facilities. And I'm pretty confident that that's true data, right? Based off just one sample, I can make that like window into like, I think it's somewhere in here. Definitely not going to be more than half. Okay, just probably not going to happen based on sampling distributions. So that's how this stuff can be used in tools and marketing in order to make sure that you're making good decisions for your company. Okay, now we have one more problem here in Chapter 8. A consumer agency wants to estimate the proportion of all drivers who wear a seatbelt while driving. The most conservative estimate, okay, we'll talk about that in just a second. What is the most conservative estimate for the minimum sample size to have a margin of error within 0.3 and 99% confident? Okay, so again, this is another margin of error question. And so again, we're going to look at just this plus or minus piece of this equation from 22. So I'm going to write that margin of error is equal to z star times p hat q hat all over n. Now the margin of error they want is 0.03. I'm going to write an equal sign this time. I'm not going to mess that one up. And then the z star for 99% is 2.576. Now this conservative estimate, okay, because I don't know, we're going to use 50-50. Okay, what 50-50 does is it proportionally is the largest n possible. And you could go through that mathematically if you wanted to. You could try anything you want. You could try 40-60, try 30-70, and you could go through all of those combinations. But what it is 0.5 times 0.5, okay, is the largest multiplication that you can do for that fraction that makes n the most conservative estimate. Okay, so what we're going to do is we're going to solve this for n. So I do that by dividing by this first. And that's going to be equal to that square root piece, right? And then I square both sides. Now in my calculator, I keep this as the answer that it is. Okay, your calculator can do that a couple different ways. I don't, even though my calculator is on fix 4, which is why I always write things basically to 4 decimal places in these videos. Even though it's on that setting, I still have it do, like when I do this next piece, n is equal to 0.55 times 0.55 over, and then I press the like second or control or whatever calculator you're using answer button so that it takes this number and it doesn't round it. It doesn't truncate it at that 4. It plugs it in there. Okay. And that's what's going to give me the most accurate answer. Okay. So I kind of follow through. I use that calculator to follow through and say like, no, I want the most exact answer that you can give me, calculator. So please do that. So that if you do that in your calculator, you're like, oh, I got something a little different than you. It might be off by like 200 or 300 actually. That's why is I followed through. I didn't just put it as this 0.0001. Under here, I said, I want you to take that as the value that it is in there. And if you have questions on how I did that, just ask me specifically in an email and I can go over that better for whatever calculator you use. Okay. All right. Our last chapter to review. Chapter 9, okay? The manufacturer of a certain brand of auto batteries claims that the mean life of these batteries is 45 months. Okay, we have this random sample of 24 such batteries and found that the mean was only 43 months. We know that the batteries have a normal distribution and the population standard deviation is 4.5 months. So since sigma is known, it is okay for me to use a z distribution in this situation, okay? Test the hypotheses with the alternative that these current batteries is actually less than 45. Okay, so that means our null hypothesis is that the mean of 45 stands. Our alternative hypothesis is, I think I might actually have significant evidence that it's less than 45, okay? Now, at an alpha equals 0.025 level, this is a one-tailed test, and it's left-tailed too. That means our critical value is going to be that z is equal to negative 1.96. Okay, so our critical value is that rejection region. Here's 45. Here's our alpha level. That would be a negative 1.96. Okay. If my data falls in that rejection region, then I can reject. So now let's look at the observed data. So z is going to be equal to 43.05 minus what I'm setting this to. So I want to figure out how far away is 43.05 from 45. Is it in this rejection region or is it not? All over. Now this is a sampling distribution, so I need to make sure I do sigma divided by the square root of n. Okay? And that z-score is equal to negative 2.1229. Negative 2 is in this rejection region. It is lower than negative 1.96. Therefore, I'm going to reject the null hypothesis. All right, let's continue with talking about hypothesis testing. Okay, 2 more problems. Okay, according to essentially the not.com, okay, the average cost of a wedding in America was almost $30,000 in 2013. A recent sample of 100 couples who got married this last year had a mean wedding cost of this data and a standard deviation of here. Now, I don't know sigma here. I don't know what the population standard deviation is. I'm going to use that sample standard deviation of 9275 to approximate the population standard deviation. When I do that, I have to use a t-distribution, which means I have to take into account my degrees of freedom. So my degrees of freedom are going to be 99. Okay, and I'm going to use that to find my critical value here. So using, again, a 2.5% confidence or significance level, do we know that the mean cost is now actually higher? Okay, so if I do that, if I look at this, since it's now higher, okay, here's mu, I now want my alpha to be on this side. Okay, and that critical value has a t of 1.984. So let's set up these hypotheses. So my null hypothesis is that the mean is 32,084, where my alternative is, hey, is it actually, oh no, I lied to you, I'm sorry, 29,858, because I have to compare it to that 2013 amount, and right here, sorry about that. Okay, I want to know, are weddings actually costing more than they did in 2013, right? All right, so let's find this observed t-value. So the observed value would be t is equal to 32,084 minus the mean all over. And then again, for our standard deviation, we have to think about this as a sampling distribution. So I need to divide this by the square root of n. And I get that that t-value is 2.41. That t-value is in our rejection region. And so I'm going to reject HO. Okay, so what that means is if you just look at data, right, and you're like, well, yeah, 32 is bigger than 29 or greater than 30,000. Yeah, but is it significantly greater, right? Like, what does it take for the sample of 100 people to have an average that is that much greater? That's what we're looking at here. So it's not just one wedding's greater, it's not just 2, it's that 100 weddings have an average that is that much greater, right? And so like, is that significant based on your standard deviation? And we have that it is, okay? You can also have hypothesis testing on proportions, okay? Now, one thing that I didn't go over in these problems is like, how do I know that it's a hypothesis test? Well, in the question, it's gonna say things like, use the significance level, can you conclude? Okay, in problem 24, it specifically said, test this hypothesis with this alternative hypothesis, okay? Whereas in chapter 8, it's going to specifically say to you things like confidence interval, confidence interval. Okay, so that's how you're going to know to do the difference between the two when you're starting this data analysis piece of the semester. Okay. All right, last and final problem for our review. According to this study, 18% of shoppers said that they prefer to buy generic, okay, instead of name brand. Suppose that in a recent sample we have 1,500 shoppers and 315 stated they preferred to buy generic instead at a significance level of 5%. So again, that's my Q, right? Significance level, hypothesis test. Can you conclude that the proportion of shoppers who prefer to buy generic is now higher than 18%? So let's go ahead and go through this and see what information is given to me. So in this problem, it gave to me that I'm going to set my null hypothesis to be that true proportion is 18. And I'm trying to test, is it actually higher? Okay. It gave me some sample information. 315 out of 1,500 gives me 0.21. Okay. And so you might think like, oh yeah, 21% is higher than 18%, but is it significantly higher, right? That's the question. So I'm going to use an alpha level of 0.05, and this is a right-tailed test. So let's think about where that rejection region is going to be. So that rejection region is going to be, if here's 18, I need alpha to be here. That's going to be, I'm doing P, so that's going to be a Z of 1.645. Okay, so now let's look at the observed data and see if I'm in that rejection region or if I'm not. So my observed data says if I take P hat and subtract out my P, and then I need to, again, think of this as a sampling distribution. So I'm going to use the sampling distribution, standard deviation centered at my proportion that's given for the population. I end up getting 3.02 standard deviations above. Okay, so this is pretty significant in the sampling distribution, right? To get an increase of 21% of these shoppers, that's pretty much significant evidence that yes, more people actually now buy generic than before. So that means that I now have significant evidence, so we're going to reject HO. Just like any of the other chapters, if after going through those 3 problems from chapter 9, you're still a little bit weary as to like, I don't really know that I understand this still completely, or you're not comfortable enough to take a final exam on it, then you should go back through all your chapter 9 materials and make sure that you review those. There's videos posted, there's example problems, so on and so forth. Again, email me if you guys have any questions or hop on to my office hours on Zoom. And I hope everybody does well, and I hope that everybody is staying home and staying safe and that everybody's nice and healthy.